So, you know, even if you never showed up to class, you should be able to at least get 6 out of 10. We'll see.
I love the trick identity one because
I said I might. Huh?
I love the trick identity one because if you knew that cosine of sine squared theta is equals to 1/2 times 1 minus cosine 2 theta, then you can just use take derivative on both sides to solve for cosine 2 theta. I mean for sine 2 theta, which would get 2 cosine times sine theta.
I didn't follow what you said.
If you knew that sine squared theta equals to 1/2.
If you know that sine squared theta
is equal to 1/2 times 1 minus cosine of 2 theta. Okay. Then you can just do derivatives on both sides to solve for cosine 2 theta. Yeah, sine 2 theta to find the trig identity. Yeah.
But the thing is x, not theta.
Did I ask you for the trig identity for something?
Yeah. Sine 2 theta.
I did for sine 2
x. So yeah, I just did derivative on both sides to solve for it.
Okay.
It worked.
It was 2 sine x cosine.
Yeah, it was. It worked. That's why I love math. They always work.
Yeah. Okay, so we're going to be continuing with 13.6. Hopefully we finished it today. By the way, I rewatched the videos for last class, and it turns out that you were right with the parameterization of the cone thing. I thought he mixed up the u's and the v's, but he didn't. It's just that, you know, sometimes I'm like writing something down or finishing a thought, and he's talking about something else. So I'm like half listening to him. So when I was half listening, I thought he mixed up the u's and the v's, but he didn't. He was right. I didn't catch anything I said about the normal vector, though. Would it matter if it's positive or negative? Because for tangent planes, it doesn't. There will be cases where the normal vector matters, but we haven't done that yet. That's when we're doing oriented surfaces. That's going to come a bit later when we're doing surfacing. Yes.
Yeah. It was double integral.
Like the r sub u cross r sub u.
Huh? That's it? Yeah, SA is equal to. SA is equal to.
Forgot the arrows, man. Well, I hope you guys didn't forget like plus c's for your integral and stuff.
Oh yeah. Things I remember.
If it's not right, it's not right.
I remember this. So I worked out.
Hey, I need to know if it's a vector. I don't know
Plus C.
what you mean by this.
Yeah.
Okay.
You have plus C for sine. Yeah.
Let's get
Yeah,
to
me
it.
too. Okay.
I thought you wanted
So recall what we've seen so far. If S is a smooth surface, parameterized by a vector function in 2 variables, right? If we're doing a 2-dimensional surface, we need 2 variables. Then we know that the general formula for the normal vector to the surface is going to be take the partial with respect to one variable, cross product that with the vector with partial with respect to the other variable, right?
Yeah.
And this is if your surface is parameterized. Now we're going to sort of bring it back to Calc 3 and say, what if it's not parameterized? What if we're given a function explicitly, right? Right? That is as a graph. For example, if I tell you that z is some function of x and y, right? I give you an explicit equation for the surface in terms of one variable, right? What would the normal vector look like in that case, right? Well, we can actually use the trivial parameterization. We're going to start to see things look familiar here.
Didn't we do this like last class?
I don't remember.
We did.
I don't think we did.
No, we did.
All right, say R of x, y, and just parameterize it by x, y, f of x, y. Right? This would mean then that your R's of x would be 1, 0 at x, and your R's of y would be 0, 1 at y. Right? This would mean that your normal vector in this case would be Rx cross Ry. So this would be what? 1, 0 at x, 0, 1 at y. What vector is this going to be? Well, this times this minus this times that, right? That's minus fx. Then it's going to be this times this minus this times that, that's minus y. And then it's going to be 1 minus 0, 1. Right? So for example, a normal vector to a graph would have that form if we just follow the theory that we've covered before. And so we will, yeah, that would be a normal. Right? So notice, for example, that this normal points up. Right? That's going to be important later. Right? Not right now, but you can know that if you apply the same theory to the graph of a function when something's given explicitly, you'll have a normal vector looking like this. And since the z-coordinate is positive, it means it points up according to the z-axis. Of course, I could take an equivalent normal vector which makes this plus, plus, minus, and that would be one that's pointing down. And there are going to be times when we want a normal vector pointing up or down, depending on the situation. But that's another section. We're going to explain that later. But your normal vector will look like this. Right? And so, yeah. And now we're going to cover surface area, and you're going to realize that familiar formulas from Calc 3 actually start to pop up after we do this. So, but just make a note of this here, that in general, normal vector to a graph might look like this. And I should mention...
What do you mean that it points up, though?
Huh?
Like, why is it relevant that it points up?
Why is it relevant?
Yeah, what's the matter if it points up?
Well, it doesn't matter yet, but in future sections it will. Because we're going to define orientation on a surface, right? So we've defined orientation on a closed curve. We know we're going in the direction of counterclockwise, right? We're going to define orientation on surfaces later, and we're going to define orientation not by which, because they're not curves anymore. We're going to define orientation by the way the normal vector is pointing.
Okay, so
if it's pointing up or down, it's going to make a difference.
So if you have a negative I and j component, then it's pointing up.
No, you look at the z.
Okay, so but
So if it's positive here, it's according to the z, it's pointing up.
Okay.
If it's negative, it's pointing down. And of course, again, like I mentioned before, you have to sort of be flexible in your thinking. The variables can be permuted. So for example, if I was given instead a function where I solve for the y, then I could get my n to be minus fx, 1 minus fz, right? There's nothing special about this formulation. You just look at what you're given, how you're given, and what you want to get to, right? And this one points up according to the y, meaning this is a normal vector that would point towards the positive y direction. Right? Now let's talk about area, which is the problem that I asked you in the bonus problem for the quiz. Definition. Your textbook derived it for you. They use Riemann sums and all that. I don't think it's really gives any insight to go into the proof. But just know that this is the case. Let S be a smooth surface. Parameterized by R of UV. For UV in some domain set D. then, right, so here I have a surface parameterized in terms of R phi v. Then the surface area of S is going to be given by that formula. That is, area is equal to the double integral of the magnitude of the normal vector.
But the
short
general
form.
formula is the big one, right?
Huh?
But the general formula is the extended version, right?
Yeah.
Okay, so if I wrote that, I got full credit.
Yes. Right. Depends on if I want you to write it out or not. But in general, that's the formula, and you can remember that n looks like this. It's also good to remember this because if we have a graph, you'll see what's going to happen. Note, if S is given by an explicit function, then you have the n you can write as minus fx minus fy positive 1, which would mean that the magnitude of the normal would be what?
Yeah, just magnitude.
Square root of fx squared plus fy squared plus 1, right?
Yep.
Therefore, the area in this case is just going to be the double integral over d of the radical of fx squared plus fy squared plus 1. And that's the formula you learned in Calc 3, right? You can actually derive it using this formula.
Weren't we supposed to learn both, though? Weren't we supposed to learn both?
In Calc 3, I don't recall them teaching you that formula.
Well, my teacher did.
At least when I taught it, I never taught that formula. In Calc 3, I showed you this, because they always ask you for a graph. Okay, so using the general form of the normal vector to a graph, we can actually derive the Calc 3 formula using the same theory that we're covering for parametric surfaces. So let me do an example. Oh, I have that one in here. What kind of surface is that?
Plane.
It's a plane, right? So I'm basically asking you to find the area of some portion of a plane given by this range of A and B. So how do we do it?
Well, just find partials.
Right, find the normal by finding the partials, right? So you have R sub u, that would give you what? 2, 0, 1. Right? That's already a constant, so if you evaluate a point, it doesn't matter. R sub v would be 1, -1, 0, right? They're already constant, so the u and v don't matter, so I just get this guy by, crossing those two, right? So I get 0, -1, you get +1. This would be 0, -1, you get, and you take the negative, right? So you get a +1. And then you have -2, -0. This implies magnitude of the normal is equal to the radical of 1 squared plus 1 squared plus 2 squared. This is radical 6, right? Therefore, the area here,
Are you sure it's right?
come again?
Are you sure it's right?
Which one?
You're not
I'm finding the cross product, it's 0 minus a -1. Is it +1?
Mine's -1.
Negative.
-1. It's negative.
Negative.
Mine's -1. Why?
Minus.
Minus negative.
It's minus.
It's
1
1.
minus 1 minus 2.
Are you talking about the first one or the second one?
Second one.
Oh, the second one you block this out. You go 0 minus 1, and then you
Yeah.
take the negative of that.
That's right.
So it's +1.
The thing is, whichever way you do it, your exponent either has to be negative or your trig exponent has to be negative, one or the other.
If you mix up, take out the second column, you'd have 2 times 0, right?
Yeah, I see.
Minus 1 times 1,
Yeah.
which is
Okay.
just 1. And then you take the negative of that.
Yeah, I wrote it wrong on my own.
Yeah. And then this one would be -2 minus 0, and you have that. Okay, the magnitude of it, you get radical 6. So you actually want to integrate the function radical 6 dA. But d was given by this. U and v range from between 0 and 1. So it's just 0 to 1, 0 to 1 of radical 6. And it doesn't matter which one I take, du, dv. Right? And that would just be radical 6. So that one was an easy example. Let's try one where it's a little bit more difficult.
You're doing a sphere now?
Huh?
So you're doing a sphere now?
Yes, that's a sphere. Right? I was going to ask you guys. Right? It sort of looks like sine phi, cosine theta, sine phi, sine theta, cosine phi. Right? So it's a sphere. What's the radius?
Actually, it's unit scale.
Right? So in that case, if you know the formula for the surface area of a sphere, you could just use it.
Actually,
But
you're
if you
right.
don't know, you can actually still figure it out, and that's what we're going to do.
Isn't that 4 over 3 pi r cubed?
Again,
Isn't that 4 over 3 pi r cubed?
that's something like that. I think so. Let's figure it out here. So let's do it the long way. So we have r sub u is going to give you what?
Cosine. So
Cosine u, cosine v, comma,
cosine u, sine v.
cosine u sine v.
Negative cosine.
Negative sine u, right? And evaluate this at the point, right? Because when you're given points, I recommend that you actually evaluate them before you start taking the cross products, so otherwise it's going to be a real pain, right? Actually, for the general formula for the normal vector, that's going to be missing. But yeah, here I want u to go between, oh no, we actually can do that. Because we're not a single point, we want a range of values. R sub v would be what? Minus sine v. Sine and cosine v. 0. So then, cross product of these guys. And what's that going to look like? Sine squared cosine. Plot this guy out, that's 0 minus this, which makes it positive. That's sine squared u cosine v, right? Plot this one out, that's 0 minus this, which would be positive.
Can we sign?
Come again?
Oh no.
Yeah, so it's 0 minus this, and so it's sine squared u sine v. Right?
It's negative.
And it's going to be negative. And then if you block this guy out, what do you get? Right, you get sine u, cosine squared v, right? Minus a negative is going to be plus times sine v squared, sine u, cosine u, sine squared v.
Professor,
Yes.
the middle term is positive.
Yeah.
It's negative.
Minus, 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 minus.
It's 3 minuses.
Someone shouted out negative. I trusted you guys. Let's check.
Negative.
Middle one, it's 0 minus a positive number, right? Because it's minus times minus, you get positive, right? And then you're going to
Minus
take the
that,
negative of
And
that.
then the minus from J.
You already told mine.
No.
It's negative.
That was the one.
Yeah.
The first minus you applied was the minus from J.
For your k component on your
Right.
new
The
vector.
k component, you should realize that you can actually simplify this, right?
Yeah, you should.
Right? Because sine u, cosine u is a common term. So you can pull this out, sine u, cosine u, times you get cosine squared v plus sine squared v, which is just 1. So that's just sine u, cosine. So that's your normal vector. This implies that the magnitude of the normal is going to give you what? The radical. If you square this guy, it's sine to the 4th u cosine squared v plus sine to the 4th u sine squared v plus sine squared u cosine squared u.
There's another pair.
Shouldn't the be this n so it's not a
There's
vector.
another pair.
You got your magnitude line.
Yeah.
It's not a vector.
You can make the sine to the 4th add over the sine to the 4th.
Right, so sine to the 4 is common. You factor it out, you'd be left with a cosine squared plus sine squared, which is 1. So you just end up with the radical of sine to the 4th u plus sine squared u cosine squared.
Professor? It is positive. It's minus a double negative, and then it's the minus from J.
Yeah, so it's 0 minus, let's sell this
A
once and for
double
all.
negative.
It will be sine squared u sine v, right?
And then the minus from the J.
And then you Right.
Yeah.
Okay, doesn't really matter.
For the normal vector, it doesn't matter. For the magnitude, it doesn't matter. But yeah, that's right. Okay. So we still get here. Just to show if the world is against you and you know you're right, you know, when you keep persisting. Everyone's like, no, it's a minus. Okay, so we're here. Now what?
Pull off the sine squared.
Sine squared is a common term, right? So your n
Sine
is
It's
just
gonna be 1.
right. You'd have sine squared from this. You're left with sine squared. Here you're left with cosine squared, and so you just have sine squared.
Yeah, that's good. Yeah.
Right? Which is pretty nice. And here you would just have what? Technically it's absolute value of sine u.
True.
But this is equal to sine u because sine is positive, since sine u is positive, non-negative. For u between 0 and pi. So your sign is positive there, so the absolute value doesn't make a difference. So this huge thing here is really just sine, right? And you're going to have things like this in your final and stuff like that,
Okay,
which is
so-
why knowing trig identities is important.
Okay, so we can memorize this actually. Just say, oh, the normal vector.
Could, but what if you don't get a number like this? You have a bunch of sines and cosines otherwise. It's possible. Right? Right? So you want to be able to figure this out no matter what they throw at you. I mean, here they throw a sphere. Yeah, it's a nice form. You can always know, oh, for a sphere, it's always just going to be sine.
And the nice thing about it is that the triple integral actually uses a sine of b, so you can remember via that manner.
Yeah, you could. Good. So now what do we have? We want the area. So area is just going to be equal to the double integral over d of sine u dA. This is going to be, and these are constants. You can really do it in any order. Say u goes from 0 to pi, b goes from 0 to 2 pi.
What did you say about doing it in any order?
I can do dv du or du dv. It won't matter because they're just constant units.
Yeah.
Doesn't matter which one you first. Right? Not going to be very difficult to set up. So this is going to give you v, right? And then you're going to plug in 2 pi and 0. So you're really just going to get 2 pi times the integral from 0 to pi of sine, which is going to be 2 pi times, what's the integral of
Negative.
sine?
It's just cosine, negative cosine.
Negative cosine between 0 and pi. So if you plug in cosine of pi is what? Negative 1. Minus cosine of 0?
Yeah, but that's negative because the cosine's negative.
Negative cosine.
Yeah, so it's actually positive.
The first one is positive.
The whole thing is negative. Just add negative to the whole thing.
No, if you plug in pi, cosine pi is negative 1.
Yes.
Times the negative,
So that's,
yeah,
yeah,
it's positive.
yeah.
And then if you plug in 0 and you minus a minus, it's positive. It's positive.
Yeah,
And
but
its area should be positive. If you get a negative area, you did something wrong. Right? So this would just be 4 pi, which is equivalent to 4, it's not 4/3, is it then? It wouldn't be 4/3. Okay, so that's that.
oh, that was volume of the sphere. Yeah,
Yeah, the 4/3 come from the volume form.
volume of the sphere.
Right? So you went here and you're like, oh, that's what a sphere is, 4/3. Why don't you? You could, right? I just have to give you 0 because it really is. You didn't show any steps and then you gave me the wrong answer. I wouldn't be able to do anything with it. If you did all this and then you made a little mistake here, then sure, I'll take off 1 or 2 points. But yeah. For examples using the other formula, a equals the double integral of fx squared plus fy squared plus 1 see your calculator notes. Or solution to not going to redo that. That's very helpful. Just want to show you how to use this new form. Okay, let's see where else. And that is pretty much the whole section. I just want to have some notes on this, like some tips. So that's this section. Basically, there are two main forms that you should come away from this remembering. The ones for the normal vector and the ones for surface area, which is just the double integral of the magnitude of the normal. Right? But there are some tricks that you should be aware of. Tips. Not really tricks. Recommendations. So there are really only a couple general formulas that we cover in this section, but they're actually pretty fundamental to what we will be doing, which is surface integrals. That's why we really need this stuff. So it's really important that you have a handle on finding normal vectors, right? So finding a normal vector shouldn't be something you think about, and it depends on what you're given and stuff like that. And also parametrizing surfaces is obviously going to be pretty important. So let's talk about something like that. Again, for things circular, like, and I'm talking about surfaces here, so when I say circular, I mean like circular cylinders, things like that. Circular, elliptical. Things sine and cosine, right? So if you're parameterizing these guys, sine and cosine in general will work. If function can be written as a graph, say f equals z of xy, etc. Then the trivial parameterization usually gives you something useful. Useful in the sense that it will give you less work. It will be less work to use it. And I'm going to give you an example of that later. I'm going to give you an example with sphere, in fact. And sine and cosine works for surfaces of revolution also, but we don't cover that really. So
Yeah, we never covered that too, right?
Something else we can talk about for planes, which again, you don't parameterize planes very much either. Use the given formula, right? So there are similar considerations. When we're parameterizing curves, we say circles, straight lines, anything else, right? They're basically the same thing for surfaces. Circular stuff, straight line stuff would fall under planes. I gave you a specific formula to deal with those, and pretty much anything else you try to use the trivial parameterization.
We never really go back to surfaces and revolution, right?
No, we're not going to cover that.
No, but when we ever get back to it, like learning Cal 2, we never learned it again.
Oh, as far as I know, I haven't seen where it came back.
Oh, so okay, so it's just gone, right?
I don't know. There might be some class where you use it, but I haven't really encountered it. Yeah. So these are the general tips for parametrizing. If finding the normal vector at a point, plug the point into RU and RP before taking the cross point. So for example, the previous problem, if I had asked you instead to find the normal vector at just a certain point, and I gave you that point, right? Instead of, I would have plugged that point directly into here before, right? So I'm only dealing with constants, right? If you're doing cross products of these huge formulas, it gives you more opportunity to make a mistake. So try to avoid doing that.
Which formula are you talking about? For planes?
Yeah.
Planes. So just give a formula. Which formula are you talking
Oh, that's the point plus a times u plus b times y.
How
I gave you
often,
this one.
how often do you run
Where
into
u and
doing
v
that?
were vectors in the group.
How often do you run into people doing that? Because that's kind of not smart.
Come again?
How often do you run into people that actually do the whole big formulas to cross products?
Oh, they might do it, right? It's like they would do this and then plug in the points at the end and then use that as a normal vector to like find a tangent thing or something. I'd recommend that once you find the RU and the RV, plug in the
Yeah.
point, then get the constant vectors and then do the cross product to find the normal. All right? Because the other way is going to give you a lot of work and you tends to make a mistake if the formulas are really big, like this one, like the last problem. Another thing is to normal vectors. Right? So you're going to be finding normal vectors all the time. So it's good that you have sort of a strategy when trying to find them. Right? Just sort of a summary. Find these in two main ways. I actually told you the two ways, right? RU cross RV, or if you can find as a graph, it's minus fx minus fy positive 1. Here's my recommendation. Case 1, right? If surface is parameterized or you have to parameterize and I'm going to talk about the have to case afterwards. Use normal vector equals RU plus RV. Right, where these guys are your independent variables. And the important thing to note is avoid this if you can. Right? So it's sort of like a force thing, right? They either have to give you the parameterization or it's something where you have to parameterize to figure it out. Right? Then you use this. Right? And try to not use that as much as possible. Because in any case where both ways work, this will almost always be hard. All right? 2. If surface is given explicitly, example, z equals f of x, y, use the normal vector equals minus fx minus fy positive 1. This of course gives you the upward form. Or n equals fx fy negative 1, the downward one. Right? And we haven't covered cases where this matters yet, but we will soon, right? So you should be able to tell the difference between pointing up and pointing down, right? Now let's talk about a have to case. And the have to case, it's pretty easy to recognize. What do you recognize about this explicit formula, right? You can find a normal if you want it pointing up or down. There are actually many cases where it's neither pointing up or down. And that's a case where you have to go back to case 1. Right? And that's the case where I'm going to show you here.
If it doesn't go up or down, I mean, if it goes like sideways or diagonally.
Yeah, well, diagonally would be up and down for different types of surfaces. Okay, so let's actually talk about.
Although if it doesn't go up or down, that would mean that it's oriented upon another axis, wouldn't it?
Depends. I'm going to show you an example.
Actually.
Right? Let's say in the question we describe a cylinder, right, with a certain height, right? And I actually want normal vectors on the cylinder, right? Your normal vector would be pointing straight out like this, right? That would be your n, right? Because it's going to be perpendicular to the surface. The problem is that doesn't point up or down. The z-coordinate for such a normal vector is 0, right? Since the z-coordinate is 0, this is not going to work, right? Because here the z-coordinate is 1. You can't fit it here to be 0. So that's an example. N would be something, something, 0. So n equals minus fx minus fy positive 1 does not work. Right? That's an example. However, that's for the whole cylinder, right? However, let's say in a situation they describe, they don't care about the whole cylinder, they only care about half the cylinder. I only care about the part of the cylinder where the y value is non-negative, right? Right? Then this would be like half the cylinder here, right? Right? In that case, how would you do it?
It would still be, I mean, it would still have a 0 for your z-coordinate, wouldn't it? Your normal vector on your z-coordinate will still be 0.
The question is, the thing is here, you'd be able to solve for y.
Because it's a function now.
Right? Example of something that would look like this as well. You would have x squared plus y squared equals some constant, right?
True.
If you only want the part where y is positive, you'd be able to say y is equal to the radical of 4 minus x squared, right? If I had the other side, I'd need a plus and minus, right? So I'd either need like 2 normal vectors to describe this surface, or just parameterize it, right? But in this case, since I only want the part where y is positive, I can literally just describe it as this function. And then I could say my normal vector here is minus fx positive 1 minus fz. And your fz would actually be 0, so that would work.
Could you
Yeah, but how would you know which one is one?
parameterization of y as the absolute value of sine?
Absolute value of what?
Sine whatever variable.
Y equals the absolute value of something?
Sine u, for example.
If you're given that y equals sine of something?
For the circle, if you only want positive values of y, would you do y equals the absolute value of sine theta, or
No. If you're thinking of parameter in terms of trig functions, you let this be 2 cosine theta, that would be 2 sine theta. And you only let theta range from this to that. You wouldn't take the absolute value of everything.
But how would you know which one is 1? Like, how would you determine which one would be 1?
I told you, if it's z equals the function,
Then it's
the
1?
z coordinate is 1.
Okay.
Y equals the function, the y coordinate is 1.
Okay. So,
X equals the function, x coordinate is 1.
okay, so it doesn't.
And I know I want positive 1 because I'm pointing in the positive y direction, right? If I took this half of this guy and my normal vectors are pointing out that way, then I'd put positive f sub x, negative 1, positive f sub z.
Would you ever make us solve it this way, or could we choose either method?
Like, if this was what you're given, this is the way I'd recommend doing it. It's
Okay.
going to be a lot less work. If this is what is given, though,
You can have
then this is not going to work, obviously, because your y would be two different functions. So unless you want to do the problem twice,
which is not allowed, is it?
which is sort of weird, unless you have a really nice function where it doesn't matter if you take the positive or negative. But here, I would just parameterize it. Just use the sine and cosine to parameterize the cylinder, and then you use one normal vector and it kills the whole problem. Right? But if it's ever the case where you can actually solve for one of the variables, I would recommend you solve for it and then do the trivial way. Right? Because then the parameterizing way, you're going to end up having to do cross products, blah, blah, blah. Here, you're only doing like partial derivatives and plug and chug. Right? So in general, this way is going to be easier. But you have to recognize when you can use these ways. And another similar situation is for spheres. All right, shows up pretty often. A whole sphere versus half a sphere. Right? So let's say I'm told you a whole sphere. Right? Now if you're finding normal vectors to this guy, right? The problem is on the top half of the sphere, the normal vectors would look like that if I'm doing outward, right? While on the bottom half, the normal vectors would look like this. Normal vectors here, they end with a positive 1. Your normal vectors down here would end with a negative 1, right?
Yeah.
You'd need two normal vectors to describe a whole sphere if you're doing it in the trivial way, right? So instead of doing the problem twice, especially if your problem is really ridiculous, I would just parameterize. And just use the RU cross RV to get the n.
Which is going to be sine.
Right? And that's going to work no matter what, because you just use your angles to rotate around the thing. It's not going to matter. However, in the situation, what if they ask you to do just the upper hemisphere?
Well, for the case of the
Right.
sphere, since the normal vector just sine of phi.
So then this guy is going to be just pointing up,
Yeah.
right?
So you could.
So I
solve-
know I only have to do this normal vector, not this one. I would actually solve for it. So instead of x squared plus y squared plus z squared equals r squared, solve for z. This means your z would be equal to the positive radical, because I will have the upper half of the sphere, of r squared minus x squared minus y squared, and then use n to be just those partial derivatives, minus fx, minus fy, positive.
Okay.
Right? And doing this would be a lot easier than the other way, because right, we actually did parameterize a sphere. Remember that whole long example we just did? So you can go through that whole long example, or this, right? So if you're parameterizing the half of a sphere, you just let the v go from 0 to pi, as opposed to 2. The u would go from 0 to pi over 2, as opposed to pi. You'd have to do that whole bunch of calculations to get to the normal vector. But if it's just the top half of the sphere, don't waste your time doing that. Solve for the z, and then just plug in each other. Right? So you're going to be presented with both of these situations. You're going to have to know which one is more convenient. This way is always going to be easier. So if you can use this, use it. Right? So if I give you the upper half of the sphere, I don't expect to see you parameterizing with sine u, cosine v, and then going through that whole rigmarole. Just solve for the z. Get the normal
Yeah, but
vector the easy way.
it should be automatic. We shouldn't have to think, right?
Yeah. Right? The idea comes from whether you can say, is it up or down? Right? The direction is going to be the determining factor. Right? So if I'm talking here about outward normals, if you look at this guy, well, if the normals are pointing out, up here they'd be going up, over here they'd be going down. I have two different directions, so just parameterize. But here I can definitely say, oh, they're pointing up. So it's definitely going to be the guy where the positive one is in the z coordinate. You just use that. We'll get more practice on this later, but just know that you can find the normal vector in two ways, but this one is usually more convenient. But you have to be in a situation where it actually works.
But it's actually on the actual xy plane though.
Yeah.
Like, for the vector that's actually parallel to the plane, it's not true, right?
Right. You won't be able to express it like this.
Yeah.
You'd have to express it with a normal vector that's 0 in the z coordinate if it's
Okay.
parallel,
Okay.
which this formula doesn't work for that situation. We'll be getting more practice with this, but no, you can find a normal vector in two ways. Either you do this, or you do something like that. You do this when you're not sure about up or down, or it's neither up or down, or it's both up and down in some situation. I would just bite the bullet and do it this way. If you're in a situation where it's definitely up, or it's definitely down, then solve for one of the variables and plug it in. Right? And again, be flexible. Up or down is relative. Right? Here, in this case, my up was to the y. Right? My down would be that way. Right? So it depends on what variable you're looking at. In the next section, we're going to see examples of that.
Oh, so done.
Yeah, we're done. So we're actually done with 13.6, so homework for that is in the next class.